Copernican principle, named after Nicholas Copernicus, states that the Earth is not in any specially favored or central location. Welcome to the principle.
It always seems like we're the center of the universe, but we're not.
There's nothing special about humans.
It's tremendous to be human. So why wouldn't we want to be in a special place in the universe, made by a special God?
Then there's cosmology.
And there are probably 100 billion solar systems in our galaxy alone.
The Copernican principle.
The universe on large scales is extremely simple. It's the same in all directions.
There's nothing special about the Earth. In fact, our universe may be one among many universes.
What our universe is really trying to tell us.
If our Earth really turns out to be special, then I would say, hey, God made a mistake.
God. That's the only infinity.
How are we going to move into the next decade?
Philosophically speaking, it's very uncomfortable. Because if the Earth is in the center of the universe, that means that somebody put it there.
We've always believed that there was a Garden of Eden.
I believe in God. I believe the universe was created by God.
We realized that maybe Earth is more special than we thought after all, but for a different reason.
We live at a very special time.
Life is extremely special.
This idea that we're not in any special place in the universe, there's something wrong with that.
All these things are rather strange, and we don't know why they're occurring right now. It's a mystery that's frustrating many of us.
There's all this stuff out there. That must mean we're insignificant. That must mean there's nothing special about this place.
On the largest possible scales, the universe is uniform.
So why would they expect to see anything special?
Just because we are smaller than a star or the Andromeda Galaxy, we're somehow less significant.
For better or worse, there's going to be a debate over this matter, and it's proper that the debate continue until the resolution has been hit upon.
Always question the scientists and their foundations.
At the moment, modern physics is not making a lot of sense.
What is everything made of? Oops, there's about 95% stuff we don't know.
And what have they discovered? Absolutely nothing. Zilch.
They've tried all the answers, and none of the answers work.
We are in a special place. I do believe that.
I don't think that this is telling us that we humans are in a particular special place.
It seems to make it special, but we don't like being special.
It's the moment of truth for science.
The principle is simple. It tells us we're nothing special. As Carl Sagan has put it, we live on an insignificant planet of a humdrum star, lost in a galaxy tucked away in some forgotten corner of a universe in which there are far more galaxies than people. Whether we call it the Copernican principle, or the cosmological principle, or the mediocrity principle, it all boils down to the same thing. We're nothing special. There are no special places or directions in the universe. No center, no edges, no up, no down, no left or right. For almost 500 years, as we have looked further and further out into the cosmos, everything has seemed to confirm this principle over and over again. And yet, we have never seen anything like Earth. A baby's smile, the finale of a great symphony. The lights of all of the cities of our Earth shining out into space. We observe these things nowhere else in all this vastness. We have yet to find evidence of other intelligent life, or any other life for that matter. If we really are nothing special, then where is everybody? Over the past decade or so, we have seen out to the very limits of the observable cosmos. We've mapped its largest structure, the cosmic microwave background, the oldest light in the universe according to the standard Big Bang model of cosmology. What we have discovered is shocking.
There is a crisis in cosmology.
It's an exciting time for cosmology because everything has changed.
We are asking about ultimate things.
Seeing the fingerprint of God or the hallmarks of the Creator.
You see, in some sense, what is happening, our concept of what the universe is has changed.
The pendulum has kind of swung all the way over and got a bit back again on the Copernican principle.
Big Bang cosmology assumes that the only thing that exists is the physical world. There's nothing beyond that.
People want to save the existing models because there's a lot that's invested in them.
The standard model is a really good model. It fits the observations very, very well.
We have a conflict between what is a well-established mainstream thought and what is the testimony of experiments.
They've essentially run into dead ends.
This is the moment of truth because they have nowhere to go.
The colors we see here in the cosmic microwave background map are kind of like a weather map showing hotter and colder, showing how hot the radiation is that's coming from different places. This is just radio noise from our own Milky Way galaxy. We're supposed to see the same number and types of hot and cold spots in all directions because there is no up in the universe that's special. And that is sort of what we see, except not quite. This map here can be decomposed into what we call multipoles. You blur out all the little spots, and you still have the bigger ones remain. Like here is an area with a lot of blue. So when you smudge it, this will be one single big blue spot. Whereas when I smudge this, where there's a lot of red and yellow, it'll be one big blurry hot spot. On the very largest scales, we see a pattern of really big hot and cold spots which line up around a special axis, which has been dubbed the axis of evil. And it's quite puzzling. Why is there a special direction in space?
Our most recent large-scale observations challenge the basic assumption upon which our modern scientific worldview rests, the Copernican principle. If the principle is wrong, it could mean that everything we think we know about our universe is wrong.
All of us are born with an innate need. In fact, it's hardwired into us to answer the question, who are we? Where did we come from? What does it all mean?
Was there a beginning? And if there was a beginning, was there a creator?
Cosmology used to be a very flaky subject, somewhere out there between philosophy and metaphysics.
In the early days, cosmology was really very much a matter of almost speculating about the universe without the data.
Because there weren't any empirical proofs for what they were finding. There were theories.
Cosmology. The study of the origins, structures, laws, and ultimate fate of the universe.
Now the remarkable thing about cosmology is that we have the data.
What counts as science and what doesn't?
Traditionally, people have said, well, once you get to the Big Bang itself, you're in the domain of philosophy or even theology. So it doesn't make sense to ask the question, what happened at the Big Bang, let alone what happened before the Big Bang.
Philosophy was useful before we had natural science. Namely, you can speculate about the origin of the universe, but you can speculate till the cows come home. But until you measure things and predict things, you don't know if they happen.
But today, we think we have it. We think we have the theory of all creation, the theory of everything.
The theory of everything. The system of the world. It has always been the dream of scientists, and earlier of philosophers and theologians, to achieve a consistent and complete description of reality. In the book of Genesis, God tells Abraham, "Look up and number the stars, if you can." This is the beginning of faith and the beginning of science. In the beginning, they're both the same thing. It was the natural assumption of the ancient world to see the movements in the heavens as centered upon us. From the location of Stonehenge, near Salisbury, England, we can see the standing ruins of what may be the very first astronomical observatory, constructed from an Earth-centered, fixed viewpoint around which the heavens revolve. If we imagine ourselves standing on a fixed world at a latitude of 51 degrees during the summer, the circle of the sun seems to rise toward the North Pole, giving us the long days of summer. Over the full course of the year, the circle of the sun will rise and fall 23.5 degrees. Add stars, and our world can be described by this diagram. Ptolemy refined a system with Earth at the center, and the puzzling back and forth motions of the planets as seen from Earth attributed to a series of epicycles, deferent and equant. The general assumption at the time was that the heavenly bodies should move in perfect, uniform circles, and Ptolemy's addition of the epicycles disturbed this metaphysical notion.
Ironically, the problem with the Ptolemaic system was a particular feature in it, which was actually, in my opinion, by far the greatest discovery made in antiquity. He had the planets moving on what was called a deferent, non-uniformly. He broke the hallowed tradition that everything must move at a uniform speed on a perfect circle. And he was forced to do that because his theory, which initially had that property, didn't fit the data.
In that regard, it should be kept in mind that if you look at pictures of medieval cosmology, then you see not only the Earth and the planets, but the outer sphere. Beyond that, you would have heaven. So that the Earth was considered to be at rest, ultimately, with respect to heaven, with respect to the throne of God.
For 1,500 years, Ptolemy's system was used as the basis of astronomy and calendars, and it worked quite well. But there were always those who detested its departure from the purely uniform, circular motion, assumed to be perfect and appropriate for heavenly bodies. Among these was Nicolaus Copernicus.
Copernicus hated that. And Copernicus set about to undo Ptolemy's greatest discovery.
While working at the request of Pope Leo X on improvements to the Julian calendar, Copernicus conceived what turned out to be the foundational idea of modernity itself, the idea that the Earth moved.
The Copernican principle is theological dynamite.
It did, in a way, all start with Copernicus, because Copernicus, we started off with the geocentric view, and Copernicus showed that that is wrong, that actually it's the sun is the center of the universe as it's seen then. The Earth goes around the sun. So then we had the heliocentric view.
Copernicus told us that we're not the center of the universe. We're certainly not the center of the solar system. The sun doesn't go around the Earth goes around the sun.
That's the Copernican principle, that if we are not really special, then this gigantic universe of ours doesn't care about us. We are nothing, absolute nothing.
In the context of cosmology, this is called the cosmological principle. So the point is that we might think we're at the center of the universe because everything should look pretty symmetric as we look around us, around the sky, but actually any other observer would see the same thing.
It's the basis of the standard cosmologies, and it's taken for granted by almost everybody in cosmology.
When Copernicus first came along and said, hey, we humans are not so special that everything centers around us, a lot of people viewed this Copernican principle as something bad.
The Copernican revolution is the revolution of the mobility of the Earth.
The Copernican principle leads to, ultimately,
The idea that there is no God.
That we are nothing compared to the splendorous universe of ours.
I think it was actually one of the greatest things that ever happened to us. We had this arrogance, and we got it knocked out of us. And we realized that actually we're not the center of everything, so we can't just say, oh, I'm not going to look at what the world looks like because I have a book here or my authority told me this is how it is. I don't need to do observations. And instead say, hey, it doesn't all center around us. We humans have to be humble. We have to look and ask Mother Nature, how do you work?
Not all were persuaded by Copernicus, however. The greatest astronomer of the time, Tycho Brahe, developed a new geocentric model. The Earth occupies the center, the planets orbit the sun, and the sun orbits the Earth.
Tycho Brahe, who is a great unsung hero of this, because he did an immense number of observations, very accurate ones, very precise for a long period of time.
Well, in the Tychonic geocentric system, the sun is traveling around the Earth literally and carrying the planets with it. So the sun is making the ecliptic, it's not the Earth.
Tycho hired a young assistant named Johannes Kepler in 1600. Kepler, working on his own development of the Copernican system, needed Tycho's observations, but Tycho refused to part with them. When Tycho died suddenly and mysteriously in 1601, Kepler took charge of Tycho's observations and used them to develop his own system.
Kepler's great insight was that the sun must be playing a significant role in the motion of the planets. They are following very definite paths, we know that for sure. How on earth do they do it? And what moves them? So he said, the sun must be somehow causing them to go round. So he postulated that the sun is rotating and had sort of spokes which somehow got weaker as you were further from the sun.
In Kepler's system, the sun is in the center while the planets move on ellipses, non-uniformly. The ellipse, with its two foci, allows us to see that Ptolemy's epicycles and equant were actually a brilliant attempt to express non-uniform motion centuries before Kepler. Indeed, once the concept of non-uniform motion is introduced, all of these systems can be shown to be geometrically identical. It was Kepler's idea that the sun must somehow be moving the planets in their orbits that set the stage for Isaac Newton's great breakthroughs. But observational tools equal to the task would first have to be developed.
Now, it's good old Galileo was the first person in the modern age who made this clear. He made the distinction between what I think it's Locke, then the philosopher Locke, described as primary qualities and secondary qualities. The primary qualities are the shapes of objects and the way they move and the space in which they move.
Galileo employed the telescope to establish that Jupiter was itself orbited by moons. This contradicted Ptolemy's idea that all bodies orbited the Earth and was seen as proof that the Earth must likewise orbit a much larger body, the Sun. For the first time, observational science claimed to have established an error in the Church's understanding of Scripture, and the first great battle between faith and science was joined.
The criticism has been made back in Galileo's time that it was the Church that was controlling knowledge, only allowing people to think within certain boundaries.
Science and theology were wed together. They were one basic entity. Theology always had the supremacy over science.
After years of house arrest, but seemingly quite sincerely nonetheless, Galileo eventually recanted.
A year before Galileo died, he rejected the heliocentric or Copernican universe that he had defended for about 30 years. A friend of his named Francesco Rinuccini came to him because he thought he had evidence from this astronomer named Giovanni Perioni to prove that the Earth was moving. And so they brought this evidence to Galileo, and Galileo said, well, there's no way I'm going to accept this. And it was a very long letter that he wrote, explaining the theology, the science, and everything he needed to explain that Perioni couldn't have found proof that the Earth was moving. Rinuccini got the letter, And as soon as he got it and read it, he erased Galileo's signature off the letter because he didn't want anybody to know that Galileo had finally repented of his heliocentric views.
However, when Giordano Bruno's ideas were similarly condemned, Bruno resisted to the bitter end.
Giordano Bruno got burnt at the stake the year 1600 for writing about an infinite space.
He was burned alive in the streets of Rome in the year 1600 for simply saying that there are other worlds out there, that there's nothing essentially special about our world. So why would the Catholic Church burn this person alive in the streets of Rome? Because think about it. If there are other worlds, then the question is, are there people on these other planets? If so, do they have a savior? If so, do they have a pope? If so, how many saints do they have? Imagine 1 billion popes, 1 trillion saints. How many trinities are there? The mind goes crazy contemplating a universe of universes. And so what did the church do? They simply burned him alive.
Bruno told his inquisitors at his sentencing, "It may be that you fear more to deliver judgment upon me than I fear judgment." Henceforth, science would increasingly assert its independence from the influence of the church. Extending Kepler's famous laws of planetary motion, Isaac Newton published his Principia Mathematica in 1687. This most influential work in all of scientific history introduced Newton's theory of universal gravitation, the first and still the greatest attempt to construct a true system of the world.
When Newton came with his theory in the late 1600s, it was felt by many people that he had resolved the whole situation, the choice between Copernicus and Tycho, by means of his equations for mechanics.
But what happened was people misunderstood what Newton really said.
But actually what Newton said was that both Copernicus and Tycho would have been wrong, because neither the sun nor the earth would be the center of the solar system or universe, but you'd have to look at centers of mass and things of that nature.
He didn't say that the smaller goes around the larger. He said that both bodies go around the center of mass. So even in the heliocentric system, it's not the Earth going around the sun. Scientifically and technically, we would say that the Earth and the sun are going around one point called the center of mass. It just so happens that Newton agrees that you could have a rotating star field, and if you do, then the center of mass is going to be somewhere in the middle of that rotating star field. And it just so happens that any object can occupy that center of mass. What that does is it nullifies the objection that the smaller always has to go around the larger. That would be true in 99.999% of the universe, but there's one place where that wouldn't be true, and that's where that star field is rotating around the center of mass.
Newton had introduced the idea of absolute space and time, which is something a bit like, as regards space, which is the more important concept, a bit like this room, a rigid framework in which you can sensibly say that a thing is moving in a straight line.
Newton's theory was based on the idea of an absolute space through which objects could be shown to be in motion. His famous bucket experiment was designed to show that motion was not relative, but had to be occurring within absolute space.
Newton had hung a bucket full of water in his room in Cambridge, and he'd wound the bucket round, and then held it still with the cord of the rope all twisted and the water in the bucket level. Then he'd let go of the bucket, and the bucket had started to spin, and its centrifugal force makes it go up the side of the bucket. And Newton argues from that concavity of the water surface can't be explained by relative motion, because when the relative motion between the bucket wall and the water was greatest, the water was flat, and when it had stopped, and there was no relative motion, the concavity was greatest.
Newton argues, therefore, there must be an absolute space that allows us to say that motion is not relative.
Newton didn't provide a mechanism. He just provided the behaviors of objects in gravitational fields. He never accounted for what caused the field.
So although it was widely thought that Newton had proven the Earth to be in absolute motion, this was by no means proven to everyone's satisfaction.
Physicist Ernst Mach provided an alternate explanation. According to Mach's principle, the Earth could be considered as the pivot point of the universe. The fact that the universe is orbiting around the Earth will create the exact same forces that we usually ascribe to the motion of the Earth. Mach's ideas would strongly influence the later development of the theory of relativity.
And Mach's principle says that you should get exactly the same effects whether the Earth is rotating in the universe or whether the Earth is fixed and the universe is rotating about it.
Motion is relative. All the objects in the universe must be moving relative to each other.
Mach's principle that because all we observe is relative motion, then once you start talking about absolute motion, that means you've imported a metaphysical principle into the system.
Mach had such absolute conviction that motion must be relative. He said, well, actually, it's nothing to do with the Earth rotating relative to absolute space. It's the Earth and the stars are in relative rotation. There's a relative rotation between them.
Rotation is relative. That is, you cannot tell by measuring centrifugal and inertial forces whether you are rotating or the universe is rotating, because you will see the same effect no matter which one it is.
And Mach then said, that's the cause of the oblation of the Earth, that it's not a perfect sphere. Whenever there is relative rotation, however you like to look at it, there will be that effect. And in fact, he goes back and says you can actually look at this from either the Ptolemaic or the Copernican point of view. You have to just concentrate on what is objectively true and say that if there is a relative rotation, then the Earth will be oblate.
By the end of the 19th century, the triumph of the Copernican system seemed complete. Only one tiny detail had eluded the experimenters. Physics at the time, including Maxwell's famous equations for electrodynamics, was based on the assumption that space was filled with a substance, an ether through which light and other electromagnetic waves would propagate. But all attempts to directly measure the motion of the Earth around the Sun through this ether had paradoxically resulted in an apparent velocity of 0. The stage was set for one of the most important events in the history of physics, the Michelson-Morley experiment.
1887 Michelson-Morley experiment. If the Earth were moving through an ether, then a sort of ether wind would be created at the surface of the Earth. A light beam projected directly into this ether wind would be expected to move slower than a light beam projected across the ether wind. If we project the beams across a known distance and then recombine them, we would expect the two waves to be out of phase by an amount that would tell us the distance the Earth had moved.
If the Earth is moving through the ether, then light waves going one direction relative to us should travel at a different speed than another direction. It's like if you're in a fast-moving river and you're swimming along with the current, you're swimming much faster relative to the shore than if you're swimming against the current. So what the Michelson-Morley experiment was designed to do was measure the speed of light in one direction versus another direction to see how fast we're moving through the ether. And what it discovered was it's the same in one direction as the other.
Michelson-Morley couldn't measure any effect of Earth's orbit, even though the assumption was at the time that that would affect the measured speed of light.
The experiment failed to detect the Earth moving in or against the ether. The problem was serious. Although various solutions were advanced, in the end, science was faced with a choice. Either discard the ether or admit that the Earth wasn't orbiting the sun. It was Albert Einstein who came up with the solution, which now forms the basis of our physics and which we call the theory of relativity.
What they thought they would discover in terms of the ether, there just wasn't any ether there. There were relative motions between objects.
Which told us there wasn't an ether, and laid the basis for Einstein's theory of relativity, which says there is no ether. That light always travels the same speed, no matter which direction it's going, or even whether it's emitted from a moving source or a source that's standing still.
So how did Einstein do it? An earlier explanation proposed by physicist Hendrik Lorentz had suggested that the measuring arm of the Michelson-Morley apparatus was being compressed by the ether in the direction of motion, just enough to make it look like we were standing still.
Lorentz says, well, the length must contract a little bit to make it look like it's the same, even though it's not. I believe that interpretation is still correct, that we do, in fact, have length contraction. He was closer to the correct explanation than Einstein's later theories.
Einstein eliminated the ether as the cause and said that it was simply a principle of nature, that when objects move through empty space, they contract in length, they decrease in the time traveled, and their mass increases, all by the same proportion, which is now known as the Lorentz transform. Hence, in order to maintain the Copernican principle, the length, time, and mass of moving objects were altered. And this is the essence of Einstein's special theory of relativity.
It was a null experiment. They were very disappointed because they couldn't measure the motion of the Earth through the ether. And Michelson himself was extremely disappointed that he couldn't do it.
And the fact that he wasn't able to measure anything was startling to a lot of people.
One of the remarkable consequences of the adoption of relativity was that every argument advanced from Galileo forward to prove the motion of the Earth around the Sun had to be abandoned. This point is made by Einstein in a book he published in 1938. The struggle, so violent in the early days of science, between the views of Ptolemy and Copernicus would then be quite meaningless. Either coordinate system could be used with equal justification. The two sentences, the sun is at rest and the earth moves, or the sun moves and the earth is at rest, would simply mean two different conventions concerning two different coordinate systems.
But if Einstein is wrong, then we had the problem that all these measured velocities of the Earth being zero stand unchallenged and unqualified. So the Earth is not moving exactly like the Michelson-Morley interferometer says it's not moving.
Albert Einstein himself said that if Michelson-Morley is wrong, then relativity is wrong.
All I have to do to shut up geocentrists is to run this experiment up on the moon and see what's going to happen. Of course, Einstein dies on the vine the second that you get a non-zero result on the moon with the Michelson-Morley interferometer, and all of a sudden that Earth is not moving, and all of physics collapses with that experiment. I think there's a reason not to put the experiment on the moon and to pretend that we already know the result and to whistle in the dark and mock the opposition.
If one day God comes down from above and says, look, these two great theories, relativity and the quantum theory, are wrong, what would I say? First of all, I would say, oh my God, all my published works are wrong. I mean, I'll have to look for another job.
And I've heard people say that the reason they don't want to publish papers that disagree with special relativity or general relativity is that they built their careers on this, and that it would be admitting a major mistake.
But second of all, once I collect my wits, I would simply say, but of course. You see, we are approaching truth, but can you actually get to absolute truth?
If you were paranoid, you'd say there's a conspiracy. Whatever it is, there is a lot of resistance to getting something published that disagrees with either of Einstein's two theories.
By the end of the 1920s, astronomer Edwin Hubble, working with the large 100-inch telescope atop Mount Wilson outside Los Angeles, had established that our galaxy was only one of many galaxies in the universe. His observations presented serious new challenges to the Copernican principle.
Well, he looks through his telescope and he sees galaxies for the first time. We had powerful telescopes back then. And not only does he see galaxies, but he sees these galaxies with what they call redshift. The wavelength of the light is now being stretched, so you see more red than you see blue.
Redshift. A shift in the wavelength of light toward the red, or lower energy end of the spectrum, giving the appearance that the light has either lost energy or has had its wavelength stretched by some physical force, as in the expansion of space.
An amazing law. When we look out at other galaxies, on average, they're moving away from us. And those that are twice as far away are moving twice as fast. And those that are 3 times as far away are moving 3 times as fast. And of course, that makes us look like we're the center of the universe, but it's not true. It just means the universe is expanding uniformly.
Now, he struggled with this. He didn't know whether to say that the redshift was a velocity indicator, that is, that the galaxies are being stretched apart from us, and that's why the wavelength of that light is being stretched so we see red, or it could be something else. You see, but he was pressured a lot by the Copernican principle to say, well, okay, let's say it's a velocity factor. The redshift is a velocity factor, and yet I'm not quite comfortable with that because that puts us in the center.
Such a condition would imply that we occupy a unique position in the universe, analogous, in a sense, to the ancient conception of a central Earth. This hypothesis cannot be disproved, but it is unwelcome and would only be accepted as a last resort in order to save the phenomena. Therefore, we disregard this possibility. The unwelcome position of a favored location must be avoided at all costs. Such a favored position is intolerable.
Hubble never believed in the expanding universe because he had the wrong value of the Hubble constant.
Hubble constant. The presumed rate at which space is created and galaxies are believed to be moving away from each other in the expanding universe theory.
Now, it's one of the most important numbers in cosmology, because once we know how fast a galaxy a million light years away from us is moving, simple physics to work backwards and figure out how long ago we were together.
But that left the centrality issue unsolved. A new idea would be required.
Friedman came up with the expanding models, which have this kind of paradoxical property that they're spatially homogeneous and isotropic, so everything looks the same everywhere and everything looks the same in every direction everywhere. And therefore, although from your viewpoint it looks as if everything is expanding away from you, from every other galaxy's viewpoint it looks as if everything is expanding away from you.
You can say that they're being expanded because you see their redshift.
People that believe in the expansion of the universe claim that it's like a muffin with raisins embedded.
Exactly as the Copernican principle requires. Imagine a cake in an oven with raisins. As the dough rises, the raisins move apart from each other, just as galaxies would move away from each other on the surface of a balloon.
So if you curve it and you put these galaxies on the surface of that curve and then you expand it,
if you're big enough that anywhere you look, it's expanding at the same rate from that spot.
Relativity tells us that in the presence of mass and energy, space can curve. Space is dynamical. It can bend, it can expand, it can contract. And one of the great holy grails of cosmology, in fact, the reason I got into cosmology originally as a particle physicist, was to determine which kind of universe we live in. Because the fact that the universe is curved means it can exist in one of 3 different forms, so-called closed, open, or flat.
The bottom line is experiment. We can simply speculate as much as we want about this great universe of ours, but the bottom line is you have to look at the data. The data shows that the universe seems to be remarkably flat. And how do you get a flat universe from a Big Bang? Well, one possibility is inflation. In fact, it is the simplest way to get a flat universe.
Inflation, the hypothesis that the universe had, at its very beginning, an extremely rapid, exponential expansion that exceeded the limit on the speed of light set by the special theory of relativity, resulting in a space that is flat and homogeneous.
Think of a balloon and put a bug on it. The bug thinks that the balloon is flat because he's very small and the balloon is very big. However, it's a balloon. It is curved. However, it looks flat only because the bug is very small. We are the bugs.
5, 4, 3, 2, 1, 0. Lift off.
We choose to go to the moon.
How is it cloudy in the TV? Oh, it's beautiful, Mike. It really is.
Coming on the heels of Hubble's discoveries, observations in the middle part of the 20th century showed that spiral galaxies didn't appear to be obeying the laws of gravity.
Several decades ago, we found a problem so great that it was brushed under the carpet for many a decade. And this is the fact that galaxies spin too fast. We believe in the work of Isaac Newton, at least on planetary scales, but when you apply Newton's laws of motion to the galaxy spins too fast. In fact, 10 times too fast. By rights, the galaxy should fly apart. Therefore, scientists said that we have to have dark matter, a halo of matter that surrounds the galaxy and holds the galaxy together.
Dark matter, hypothesized form of matter introduced to allow conventional theories of gravity to explain the observed anomalies in galaxy rotation and expansion.
I mean, if you're going to use Newton's laws, F equals ma, and you're going to use Einstein's tensor equation, then you better have the matter and energy in the universe to make it work. But it ain't there.
Between 1 and 3% of the universe is all the stuff we can see, and somewhere between 99 and 97% of the universe is stuff we can't see. This dark matter that dominates our galaxy, we're virtually certain now, is made of some new type of elementary particle, different than the stuff that makes you and I up.
And what have they discovered? Absolutely nothing. Zilch.
What is a little bit perturbing is that after 50 years we still haven't found what the dark matter is. But on the other hand, that doesn't mean they're not there, it just means they're harder to find than we thought.
Turns out the gravitational energy of every galaxy moving away from us is 0. And that's strongly suggestive that the universe actually came from nothing. In fact, every measurement we can make about the universe is really consistent with a universe that came from nothing.
Nothing, generally understood as the absence of anything, but sometimes used in modern cosmology to refer to an unseen form of something, virtual particles and the quantum vacuum.
Something from nothing, a key concept in modern cosmology. But this turns out to be a very unusual kind of nothing, since it apparently contains at least 2 somethings, energy and a law of gravity.
Well, it's a strange time in cosmology. It's an interesting time because we don't understand anything, or rather, we don't understand nothing. Because it turns out nothing is almost everything.
If you understand nothing, you understand everything.
Turns out the dominant stuff in the universe is nothing, and we don't have the slightest understanding of why. Nothing is really not quite nothing. Nothing is really a boiling, bubbling brew of virtual particles that pop in and out of existence in a timescale so short you can't actually see them. Now, you might say, if they exist for a time that's so short you can't even see them, it's like counting angels on the head of a pin. It's like philosophy, it's not like physics. But in fact, while we can't see those virtual particles directly, they do have an impact, an indirect impact on atoms and the structure of atoms in a way that we can actually predict.
So we now realize that nothingness is foamy, is foam created by subatomic particles darting in and out of existence. Well, if subatomic particles could do this, why not universes? We now believe that in the quantum foam, baby universes are constantly appearing. So if I had a super microscope and could look down at the fabric, the instantaneous fabric of space-time itself, I would see a bubble bath with baby universes being formed all the time.
If you have nothingness, quantum fluctuations will always produce something. And when you add gravity in the mix, it's even possible that whole universes could come from nothing.
Big bangs happen all the time, but most of them don't get anywhere. They pop back into the vacuum. But our universe was special. Our universe, for some reason, popped out of nothing and just kept on going.
So not only is all the evidence suggestive that we came from nothing, but the laws of physics tell us that it's to be expected that something comes from nothing.
They impose on the science, on their observations, they impose their worldview, which is really their religious belief system.
So the problem with cosmology is that we keep inventing theories, ad hoc theories, to try to explain the data, such as inflation, dark matter, dark energy, and so on, just to keep patching the theory up.
The energy of the vacuum, dark energy as we call it, is the greatest mystery in all of creation.
Dark energy, a hypothetical form of energy that allows an accelerated expansion of the universe.
Nobody knows what the dark energy is. There are thousands of people out there trying to work out what the dark energy is.
What they do is they have to invent it now. And if you've ever read the science magazines, they say, well, there's dark energy and dark matter out there, and they constitute 96% of our universe. The reason they say that is because they need it. It's not going to work. Their Big Bang universe is not going to work without that matter and energy.
The necessity of adding unobserved entities such as dark matter and dark energy to the Big Bang theory might be a sign that there is something wrong in the fundamental assumptions.
In our universe, we have two great theories. God, in some sense, has a left hand and a right hand. The theory of the big and the theory of the very small. The theory of the big is relativity. It gives us black holes and big bangs and things we can see with the naked eye in outer space. Then there's the quantum theory, the theory of the atom. Now, the juncture between the two, that's when all bets fail.
And it actually is split into two giant sides, the relativity side for the large and the quantum side for the small, and we haven't been able to unify all these things back together again.
There is a crisis in cosmology.
Because the quantum field theory, it says there's this vast amount of energy in the quantum vacuum. If you do a simple-minded application of that to general relativity, it tells you the universe should be accelerating an incredible number of orders of magnitudes faster than it is.
Usually in science, if we're off by a factor of 2 or a factor of 10, we call that horrible. We say something's wrong with the theory. We're off by a factor of 10. However, in cosmology, we're off by a factor of 10 to the 120. That is 1 with 120 zeros after it. This is the largest mismatch between theory and experiment in the history of science.
Recently, some theorists have proposed that the need for dark energy can be dispensed with if we dispense with the Copernican principle itself.
There's an important point here, because if you then said, okay, let's stop here for a minute and let's suppose dark energy doesn't exist. Now, the raw data is correct. It's what we observe. But let's just change the model a bit. Let's say, okay, let's suppose for a minute that the universe is not homogeneous.
Or, to put it another way, let's suppose the universe does not follow the Copernican principle after all.
Let's see if we can fit exactly the same data with no dark energy. And the answer is yes, you can.
If we assume that Earth is in a special position, near the center of a local void, we can account for all observations without the necessity of dark energy.
This is using a description of the universe that has us somewhere near the local center, a spherically symmetric universe. But when you apply that type of a model, it actually does fit the data without dark energy.
What I'm saying is that is a possible alternative which needs to be looked at.
Among the recent large-scale surveys of our universe, the Sloan Digital Sky Survey has given us our most complete look to date at the distribution of galaxies in the sky. Professor John Hartnett has researched these galaxy distributions and has discovered evidence of non-Copernican periodic structure in the galaxy distributions.
We looked at of the order upward of over 400,000 galaxies and sort of posed the question, well, how are these things arranged in the sky? These are a three-dimensional map, and had a look at whether or not there was any structure in that. To my surprise, the mathematics bore out, and there is some very unusual structure. Now, if you look at a picture of this map, when I first saw that, it looked to me like there was like concentric shells, as if the galaxies preferred to lie at some periodic spacing out from the Earth. This is sort of like saying that our galaxy is somewhere near the center of the universe, and when you look at the galaxies arrayed all around us, they're on sort of like giant shells. They prefer to lie on these concentric shells spaced out by around about 250 million light-year separation.
One of the chief difficulties faced by cosmologists is that as we look out at the cosmos, our view is partially blocked by our own Milky Way galaxy. We are able to see only about a quarter of the whole sky. As we pull up from Earth, we see the two pie-shaped wedges which constitute the data of the Sloan Digital Sky Survey. Each one of these dots represents an entire galaxy, containing on average hundreds of billions of stars, giving us a visual indication of just how astonishingly vast our cosmos actually is. As we look down upon this two-dimensional slice of the sky, we notice that there is regular, periodic, concentric structure with a preferred redshift spacing or interval, or delta Z value, between each shell of approximately 0.0246, or about 250 million light years. If we fill in the missing areas of the sky on the assumption that the distribution is more or less similar, we are in a position to get a look at how the whole 3D structure might appear as viewed from Earth. The first thing to notice is, if we looked at the universe from some point far removed from our location, we would not see the same concentric shell structure, which is directly contrary to the assumptions of the Copernican principle. In 3D, we can slice open the galaxy distributions almost as if we were looking at the layers of an onion, disclosing the concentric shell structure around us.
So every phenomenon that you see out there in the universe is all in concentric cells around where? The Earth. I mean, how do you avoid this evidence?
Whether it would lead to an Earth-centered universe in itself, I'm not that sure, and because it certainly leads to our galaxy maybe being in a special place.
Now that is controversial because anyone in the standard cosmology community would not even entertain such a notion.
Cosmologists should be open-minded and not suppress, if you like, the exploration of non-mainstream ideas.
The oldest light in the universe, according to the Big Bang Theory, is the cosmic microwave background, the leftover radiation from the Big Bang itself, the only source of radiation we've ever discovered that comes to us from all directions of the sky.
The cosmic microwave background is the afterglow of the Big Bang. It's the radiation coming at us from the Big Bang, the leftover radiation. It's amazing. In fact, it's highly visible in a sense, but it wasn't discovered until 1965 in New Jersey, of all places, by two people who didn't know what the heck they were doing, but they won the Nobel Prize anyway. But in fact, you've actually seen it. Well, if you've ever disconnected your cable TV, or if you're like me, old enough to remember before cable TV, when the stations went off the air at night, after the test pattern, there'd be static. If you disconnect the cable on your TV, you'll see static. Turns out about 1% of the static you can see in your TV is radiation left over from the Big Bang.
This background radiation should be isotropic. It should define no special direction in the universe, and certainly not one related in any way to us. Max Tegmark decided to look at the cosmic microwave background in a new way. And he discovered something amazing.
I decided to look at the data in a different way by separating it into what we call spherical harmonics. And each one of those harmonics corresponds to a picture you can look at on your screen. And I wrote this computer program, and like 3 in the morning was done, and I hit enter, and poof, up came a picture, and whoa. Crazy. I had typed in 2, which was the lowest one of these modes, and it didn't look at all like it was supposed to do. I had looked at this because there had been previous papers saying maybe there was something a little fishy about this lowest harmonic, but nobody had ever made a picture of it before because they couldn't clean out all the junk. And checked my program, there was nothing seemingly wrong with it. So I thought, I'm kind of tired, but I have to type in 3 and see what the next one looks like. And that one looked even more crazy. It had this big band, like a pancake across the sky. And it was lined up with what came out when I had typed in 2. Like, whoa, what is going on here? So we mentioned this sort of in passing at the end of our paper, that there was this funny alignment which later got dubbed the axis of evil. And we did another paper and realized that it's actually quite unlikely that it's just a fluke. And then later on, other people, like Dragan Hutterer and many others, picked up on this and did much more careful studies and found that actually there was nothing wrong in my computer program, and the effect was there, and even more strongly so than we had guessed.
When you look at the cosmic microwave background, it's uniform in all directions, which is what you'd expect for the universe, in fact. Another bit of evidence that there really was a Big Bang. But there have been some anomalies.
There's one point about it that the radiation isn't exactly isotropic, it's almost.
So they send up the satellite and they find out, wow, there's anisotropies out there. It's not smooth. Not only did they find anisotropies, what they found was that these anisotropies, these disturbances, these temperature disturbances throughout the universe were all pointing to the Earth.
This is, if you just look at the galaxies out there in the universe, it doesn't matter whether you look at them like this or whether you tilt your head like this or like that, because there is no special direction. There's no up or down in space.
One of the fundamental principles of cosmology is the Copernican principle, that we believe that the Earth does not occupy a special position.
Yet, there is this very special direction imprinted in these baby pictures of the universe. And it's pretty clear now, since many different groups have hammered at this, that it's real. It's in there in the data. What's much less clear is what it means.
The cosmic microwave background alignments do not define a center, but instead an axis, a preferred direction spanning the entire universe. The fact that these alignments are correlated to our own neighborhood is highly difficult to explain from within the assumptions of Big Bang cosmology. The dipole, which is aligned with our equinox, is usually attributed to a relative motion between our solar system and the cosmic background itself. However, the quadrupole and octopole alignments are also with respect to the ecliptic, the plane of the orbit of the planets around the sun.
Some people have actually suggested that there's structure in the cosmic microwave background radiation that's related to where the Earth is and how it's going around the sun, which is crazy, because we're nothing special.
Professor Lawrence Krauss, writing back in 2006, addressed these strange anomalies in the cosmic microwave background as follows.
He says this, but when you look at the CMB map, you also see that the structure that is observed is, in fact, in a weird way, correlated with the plane of the Earth around the sun. Is this Copernicus coming back to haunt us? That's crazy. We're looking out at the whole universe. There's no way there should be a correlation of structure with our motion of the Earth around the sun, the plane of the Earth around the sun, the ecliptic. That would say we are truly the center of the universe, unquote.
In 2005, I was talking about the observation and what it would imply, but it's so strange that it's likely to be wrong. Now, that doesn't mean it's always wrong, and some things are so strange that they're actually right. But in this case, I suspect that the structure that was seen by some people that suggested that, you know, the whole microwave background is arranged around us is probably not right.
If you run up against an interpretation that sounds viable and credible, that's not Copernican, it's thrown out.
And so I can see the resistance there, you know, that if you, like a heretic, you know, you come out and you say, hey, no, this is not right. There is evidence that this cosmological principle, this idea that we're not in any special place in the universe, there's something wrong with that.
That whole cosmic microwave background is pointing to us, this tiny little space in the universe, and that happens to be where we live.
I frankly try to keep an open mind about what this ultimately means, because I still don't know.
As a matter of fact, you can go on some websites of NASA and see that they've started to take down stuff that might hint to a geocentric universe.
You know, whenever there's something weird, it's wonderful if you get a fresh measurement of it. So I'm really keen to see what the Planck satellite pictures are going to look like, if they are going to have the same weird alignment. And they're going to have even better ability also to clean out noise from the galaxy and other sources. So I'm keeping all options on the table until then.
The strangeness of the alignment of cosmic microwave background with the ecliptic and equinoxes of Earth led many cosmologists to believe that the Planck satellite mission would finally show these alignments to have been a mistake, a foreground that wasn't subtracted properly, or a scanning beam anomaly in the WMAP telescope. Would the axis of evil turn out to be real? Finally, on March 21st, 2013, at the headquarters of the European Space Agency in Paris, the results of the Planck satellite mission were publicly released.
Today we are going to present to you the cosmic microwave background. Progress towards the future by understanding the past. This map is a goldmine of information.
The stakes were high. If Planck were to confirm the existence of the axis of evil, it could mean the foundational principle of modern cosmology, the Copernican principle, is wrong. Planck was expected by many to show instead that the strange CMB axis of evil was nothing more than foreground contamination or a scanning beam anomaly somehow missed by the WMAP team. We flew back to Boston to interview Max Tegmark at MIT. We asked him whether his discovery of the axis of evil had been confirmed or debunked by Planck.
It was just so exciting. I'm standing there shaving at 5 in the morning while I'm watching George of Staffview on the live feed press conference. And when the first image comes up on the screen, I line it up with this cleaned image of the data that we had made way back in the past. And it all matches. This spot matches this spot, this one matches this spot. And I'm thinking to myself, whoa. This is so awesome. And the axis of evil is obviously there because all the big spots are in the same places. So all these puzzling anomalies have survived. And the axis of evil is still with us. And we have to actually ask us what it means.
But what about the alignments with the ecliptic and equinoxes, which Lawrence Krauss had said would mean we were really the center of the universe? We asked Max Tegmark if Planck's results had convinced him that the axis of evil actually was aligned with our ecliptic and equinoxes.
I have to confess that I was bothered by the fact that the axis of evil seemed linked to a special direction in our solar system. And something in my gut was telling me that this might, even though I greatly trust the people on the WMAP team, point to something fishy in their analysis. But I also feel very strongly that I have to actually override my gut by using my brain and by looking at data. And now we have completely independent data with better detectors, completely different people seeing the same thing. So there's just no way we can blame this on the WMAP team. There is, I think, a real possibility that the axis of evil and other strange things we see in the large scales of the cosmic microwave background are a hint of something really big, just the tip of an iceberg, something huge.
So now we're in a position to look at the entire microwave sky. First, we introduce the multipoles. The dipole, usually attributed to a relative motion between our local system and the CMB itself. The quadrupole, the north and south ecliptic poles, and the spring and fall equinoxes. The S-shaped line represents the plane of the ecliptic, the plane of the orbit of the planets around the sun. Notice how it neatly divides warm and cold sections of the CMB map. This is our first hint that something very unusual is going on. Now we transform our Molveda projection into a sphere and rotate our universe so that the S-shaped line of the ecliptic becomes the dark line across the center of the sphere. This plane, lying between the warm and cold areas of the CMB, will become the grid along which we fly through the entire visible universe. From the point at which space first becomes transparent and structure begins to form, through the Virgo supercluster, and finally to our own Milky Way galaxy. As we enter it, amazingly, we arrive at our own local neighborhood, our sun, and finally, our home. So does this mean that the pendulum has started to swing back away from the Copernican principle? Could this, in fact, be Copernicus coming back to haunt us?
Now today, fortunately, we don't burn astronomers alive anymore, which I think is a good thing.
Life may be very rare, and we may be very special, but that doesn't mean the universe was created just for us.
I've really changed my opinion in a major way and how I feel about our place in the cosmos. For many years, I was feeling more and more insignificant. We realized that we humans were just living on a small planet in a solar system, in a galaxy, in this universe. We just kept getting smaller. Then we realized we're not even made of the majority kind of substance, dark matter and dark energy. And then we realized that we're also very brief. Our 100-year lifespans, compared to the 14 billion year age of the universe. So how could we possibly be significant? But I've really completely changed my mind, and now I actually think we're very significant.
The very successes of science have led it to this moment of truth. It now confronts the very same questions which were once considered the domain of metaphysics, even of theology.
We are asking about ultimate things. What is the bedrock of the world? What is time? What is motion? These are the most fundamental things.
Oh, this cosmic microwave background is like we are seeing the fingerprint of God, the hallmarks of the Creator.
Because nobody believes that the universe comes to an end just where we can see.
It's been remarkably difficult to come up with any physical theory that just makes exactly what we see and then stops.
I'm a great advocate of the multiverse and the idea that, our universe is just one of many, this progression in the Copernican concept.
Multiverse. The hypothesis that an unending number of universes exist, the main purpose being to answer what is commonly understood as the fine-tuning problem, namely, that our single universe operates within a very narrow margin of physical constants and could not have come into existence by chance.
We are made out of electrons. If each electron is in multiple places at the same time, then am I not also multiple places at the same time? And the answer is yes. Now apply this quantum principle to the universe. If the universe obeys uncertainty, then you don't know where the Big Bang was. The Big Bang could have been here, the Big Bang could have been there, just like electrons. You don't know where the electrons is. So this means you have multiple universes. So as soon as you apply the quantum principle to the universe, immediately you get parallel universes.
And some people don't like it and call it a crisis. I call it a multiverse.
I think the multiverse has really come about because of a whole range of fine-tuning issues. The Goldilocks type universe, the laws of physics finely tuned, the existence of humans.
The multiverse is an attempt to take quantum mechanics and give every possible answer as a yes.
There could be an infinite number of universes, and the energy and empty space would be different in each one. And only in those in which the energy empty space is comparable to what we see would galaxies have formed and life would have formed. So it's kind of a cosmic natural selection. It's not fine-tuning, it's not religious, like some people think. It's the opposite.
Yes, it can get all sorts of answers predictively, but it doesn't provide the mechanisms and it doesn't determine things properly.
There are actually a variety of approaches that come from both cosmology and from particle physics, which predict that there could be many other universes.
By inventing all of these other universes that are unobservable, unverifiable.
If you have a mechanism for producing one Big Bang, it's going to produce other Big Bangs, and therefore it would seem fairly logical there should be many other universes.
The multiverse hypothesis, the problem in a sense is it can explain too much. In a multiverse, as various people have proposed it, anything you want happens here, something else. You can take anything you want and you can explain it by the multiverse. That means it has incredible explanatory power, but it also means there's effectively nothing you can do to test it.
In trying to figure out all these anomalies that they see in the universe that don't fit the Copernican principle, what this leads to is creating a whole bunch of universes, billions and billions. It goes on ad infinitum. Somewhere in all those universes, there's going to be something that's not geocentric, you see, and that's how we can get out of the problem.
There's a geocentric universe in the multiverses. There's a heliocentric one. There's a jovocentric one centered on Jupiter by this hypothesis.
It's a very, very interesting hypothesis. One can make good reasons why it's a good model to believe in, but there isn't any direct way to prove the multiverse is correct observationally.
We cannot directly observe these other universes because, remember, the point is we cannot observe beyond 40 billion light years.
Got to be careful when we claim the mantle of science for some of what comes out. I'm very happy to claim the mantle of scientifically based philosophy for what comes out, but I'm worried when we're claiming the mantle of science.
The fine-tunings, if we're the only universe, the fine-tunings are really hard to explain unless you're going to invoke a creator or something.
We seem to find ourselves in a part of the universe that is perfectly tuned for life.
On the other hand, if you have got a multiverse, then it's fairly natural by a simple selection effect that we are going to be in one of the universes which is going to allow life to arise.
Saying there's many universes doesn't really answer anything, does it? Because it doesn't deal with the universe we're in, assuming it's even true.
Where are we going to find ourselves in the multiverse? The only place we're going to find ourselves is where we can survive.
I would agree that the alternative is between a multiverse and God.
It's just too perfect to be a happenstance or a coincidence.
The reason the universe appears to be so tuned for our existence is not because some divine intelligence decided, I want to create a universe so people can be in it, but rather, if we're any different, we wouldn't be here.
Once you eliminate the creator, you have this gradation of learning, and all of a sudden you reach this point where you can't go any further.
The universe could not have been an accident. It is so gorgeous when it could have been random and ugly. It is so beautiful and elegant when it could have been random and an unwieldy collection of subatomic particles. Here it is, this glorious universe of ours that creates consciousness.
To me, that's evidence of a creator behind it.
What is particularly worrying about some of the discussion of the multiverse is the use of the word infinity.
God. That's the only infinity.
Infinity is a number that can never, ever, ever be attained. Infinity is the unattainable.
Big Bang cosmology assumes that the only thing that exists is the physical world. There's nothing beyond that.
You don't confront the face of God in a multiverse. You're just the result of a mathematical equation splitting infinitely.
If that were true, there would be no room at all for spirit, or for God, or for any of the mutual interactions.
People have had a brick wall placed in front of them because science has said certain things, and they said, you must stay over in this category here, and you cannot go into the God category because that's going to destroy our science.
It does tend to be taboo to call on God or a creator for anything in science.
And there's no evidence of planning or purpose in the universe as far as we can tell.
They're not really referring to a Genesis biblical creator. They're referring to some innate, inanimate universe that created itself.
So George, if you do take the fine-tuning seriously, but you don't believe it actually is due to there being a multiverse, what is your explanation of the fine-tunings?
You really want to push me on this?
Even if it's a non-scientific explanation.
It's absolutely possible that there is a multiverse. It's possible this was just the way things happened, that there's nothing more to say about it. It's possible that in some sense it was meant to be that way, and that in fact all the other evidence about meaning, purpose and so on in the universe might help one to say that there's some element of meaning underlying all of this.
But is that tantamount to saying that there was a fine-tuner, a creator?
That would be tantamount to saying that.
And so, at the end of the day, the question remains, are we significant or just a cosmic accident?
Well, I think it's now very well established that our universe is a very special universe within the space of universes we can imagine.
When you look at all the parameters that have to be just right, temperature, solar radiation or stars radiation nearby, etc. So when you really look at the details, it takes a phenomenal number of parameters to be correct in order to support life on the Earth. When I see how barren the other planets are and how bountiful the Earth is, something's different, and we're in just the right spot for it.
We've got to get away from that Copernican principle and the notion that man means nothing. From just a meaningless molecule to a human being that's in a special location for presumably a special purpose, and therefore men are driven by their purpose, and they can see themselves in a very different light than the fact that they are simply chaotic blobs.
So that according to Big Bang cosmology, the future looks very bleak. Either the universe is going to keep on expanding forever, and eventually it'll run out of energy and all life will die, or it will recollapse again, and then everything will die as well.
The two lessons of cosmology that I like to give people are, one, we're more insignificant than we thought we were before. You're completely insignificant. All of our human drama and everything else is more irrelevant when it comes to the cosmos than it was before. So we're insignificant and the future's miserable. So those are the two things we've learned.
One shouldn't be too pessimistic.
Because astronomy is ripe for a new Copernican revolution, perhaps back in the other direction.
The Earth is a very special place, no two ways about it.
Human beings are very wonderful.
You are so special that consciousness is so powerful and so hard to create that is the defining principle of the universe itself.
But if we are significant, and if there's something special about our home, this planet, then those concepts have tremendous implications. And we need to be then focused on our commitments as stewards over the creation that we have.
We need to take that brick wall away so that we can make that bridge between science and theology.
I have a minority view as to what this means. I think it means that life of the advanced form we enjoy here is extremely rare, and that we are in fact the only life in our entire observable universe that's gotten to the point that we have telescopes. And if that's true, then we are very significant.
The carbon, the nitrogen, the oxygen, the iron in your body wasn't created in the Big Bang. It was created in the fiery nuclear furnaces of the cores of stars, and the only way it could have gotten into your body is if the stars exploded. So, and the atoms in your left hand might have come from a different star than your right hand, and so you're not only are you intimately connected to the cosmos, every atom in your body has experienced the most cataclysmic explosion in nature, a supernova explosion. When a star explodes, it burns with a brightness of 10 billion stars, and every atom in your body's experienced it.
So what I take away from this is we simply always need to keep an open mind and listen to all viewpoints and let Mother Nature be the one who gets the final word.
There's always a revolution coming in science because science is necessarily provisional. It cannot make a final statement because it doesn't know everything. It cannot examine what's going on at the four corners of the universe.
As to how many angels dance on the head of a pin, I think it's still an open question.
You know, I can tell you what the future might be, but it could be something different.
I mean, it's absolutely extraordinary. When you look at it, there's this little ball of rock with this thin layer of air, and here we are dependent on the rock and the air and the sun floating through these immense space. I just think one ought to have that picture of what we are in order just to have a full concept of being a human being.
We also know that there's nothing about the laws of physics that says that life has to be limited to just being stuck on this planet and can't ultimately engulf our entire universe, come alive. If that happens in the distant future, I think it will be because of what we humans decide to do here on this planet. And it's probably going to be settled in my lifetime, whether we just permanently screw it up or get our act together and concede space with life. And if in the distant future our whole universe has come alive, I don't know how our distant ancestors are going to think about us, but I'm sure they're not going to think of us as insignificant.
For nearly 400 years, ever since the trial of Galileo, there has often been tension, if not outright conflict, between faith and science. Remarkably, the Copernican principle seems to be the ground upon which faith and science are again, at long last, approaching one another. Perhaps we can hope to achieve a more fruitful and successful dialogue this time around.